Hello, welcome to this very first lecture on geophysical fluid dynamics. Before delving deep into the course materials, we will first go over the modules of this course, modules or the subsections that I have divided the course into, and these will be roughly divided each into 3 weeks, and total there are 4 modules as I see it. So let's go over the modules first. So first module is understanding the dynamics of geophysical flows and developing an intuition for the governing equations. Okay, so this is what this is where we will develop the governing equations of fluid flow that are relevant to geophysical applications, and then we will do a scale analysis, and we will discuss some non-dimensional numbers which give us the ratio of different physical quantities, and we will see how the dimensional values of, or how the magnitude of those non-dimensional numbers actually dictate how the governing equations can be further simplified. Then in the next module we will discuss vorticity dynamics. We will and then understand the properties of surface, internal and topographic waves in geophysical flows. In the third module we will have a brief introduction to instabilities, hydrodynamic instabilities, and then we will discuss instabilities which are relevant to geophysical flows, that is, those instabilities that are controlled by shear and or stratification. So shear is the change in the velocity with in a certain direction, and stratification is the change in this case we will be discussing density stratification. Let's see, that means this change in density with a certain in a certain direction. This is mostly in the vertical direction that we will be concerned about. In the last module we will be discussing turbulence, and geophysical flows being of very high Reynolds number are routinely turbulent. We'll discuss some turbulence systems, we'll discuss turbulence modeling, and we will discuss a quantity called the turbulent viscosity or the eddy viscosity. We will also discuss atmospheric and oceanic general circulation and how numerical modeling can be used to understand geophysical flows, that is, flows in the atmosphere and the ocean. So as I have mentioned multiple times, geophysical fluid dynamics deals with large scale atmospheric and oceanic flows. So these are flows around us. This make the flows in these atmosphere in the ocean makes life possible on Earth. So these flows, as I have again mentioned in the introductory lecture, introductory video, that these flows are affected by the rotation of the Earth about its axis. We all know that the Earth is not stationary. It is rotating about its axis, and it's also revolving around the sun. But the geophysical flows are strongly affected by rotation of the Earth about its axis, and we'll see that this gives rise to interesting properties. And they are also affected by the variation of density with depth or height. This is again something that I have already mentioned. So density is a function of temperature or salt concentration in the fluid. It can also be a function of pressure and the concentration of other particulate matters in the system, and this varies with depth or height in the ocean. But before delving deep into the dynamics of the oceans and the atmosphere, it is important to understand why oceans and atmosphere are interesting, why they are important for us to study. So the oceans hold approximately 95% of the total water on Earth and covers approximately 70% of the global surface. Oceans are the source of approximately 85% of global evaporation. Water vapor condenses into clouds and falls as precipitation, releasing latent heat that again drives atmospheric circulation. The ocean produces huge amount of planet's oxygen. This makes life possible on Earth, and hence it also supports a lot of Earth's biodiversity. The air-sea exchange of carbon dioxide and dimethyl sulfide can significantly alter atmospheric concentration and cloud formation. The ocean is not a passive entity which is just sitting there. It is actively talking to the atmosphere above it. And how is it talking? By air-sea exchange of gases, which affects the atmosphere. Ocean also is redistributing the heat that it is gaining due to solar radiation, and this keeps the planet habitable, particularly at higher latitudes. So this is an image, satellite derived image of the surface temperature, this temperature at the surface of the ocean, and this is the United States east coast, and this current that you see here is known as the Gulf Stream. So this is a stream of current, this is a current that takes heat from around the tropics, and it is taking, as you can see, towards higher latitudes. So the color shows temperature. Now the atmosphere, which is again a crucial part of our Earth, which makes life possible on Earth, and the geophysical fluid dynamics includes both studies of the atmosphere and the ocean. So now you're understanding why the atmosphere is important. So the atmosphere is a layer of, what is atmosphere? First, the definition. Atmosphere is a layer of gas and some suspended particles that surround the Earth and are held together by Earth's gravity. So this can contain a lot of gases, mostly it's nitrogen, oxygen, and some other gases in smaller quantities like argon and ozone. And the atmosphere protects us and from the outer space, and this makes life possible on Earth. By comparison to the size of the Earth, the atmosphere is very thin, but still this thin layer is something which is protecting us from harmful radiation that are there in the outer space, and this is why we can survive, human beings and other life forms can survive on Earth. The atmosphere is divided into distinct layers called the troposphere, stratosphere, mesosphere, thermosphere, etc. So this, on this left hand side, is showing you a schematic of the different divisions that we have created in the atmosphere, based on in this case based on the temperature profile. So this is so this yellow lines, this curve is showing you the temperature distribution in the, it's a schematic in temperature distribution in the atmosphere. So the atmosphere, as you can see, is a few hundred kilometers. So the troposphere is the one where we live, and this is the surface of the Earth, and the temperature linearly decreases, approximately linearly decreases to about -50, -55 degrees centigrades to the end of the troposphere, which is called the tropopause. So which is at about something around 8 to 12 kilometers, 15 kilometers, depending on where on Earth you measure the tropopause. It varies from poles to the equator. And then there is an increase in the temperature from the tropopause in this other zone, which is called the stratosphere. So the troposphere is something which admits weather phenomena, and this is where all the weather phenomena happen. This is where we live. This is where most of the Earth's surface, I mean, the tallest point is below the tropopause on an average, and most of the phenomena that are happening on Earth are happening in this troposphere. Thermodynamically, the atmospheric properties can be modeled as an ideal gas under normal conditions of temperature and pressure. So this term thermodynamically is important because we'll again come back to it when we delve deeper into the dynamics of the atmosphere. So now there is an important question: what are the differences between atmospheric and oceanic flows? We know that geophysical fluid dynamics comprise both atmospheres and ocean. So the oceanic flows are affected strongly by land boundaries, which is not a constraint in most of the atmospheric flows. As you could see, the atmosphere is of hundreds of kilometers, and it flows over the Earth's surface, whereas the Earth's surface has undulations which are very small as compared to the total height of the atmosphere. Whereas oceanic flows are bounded by continents, by countries, so by land masses, and hence they are strongly affected by these boundaries. The atmospheric flows are primarily thermodynamically driven. Solar radiation heats up the land and the ocean, which in solar radiation heats up the land and the ocean, which in turn heats up the atmosphere from below. So the atmospheric gases are transparent to the solar radiation, so they come down and heat the land and the ocean, which in turn releases long wave radiation, which is being trapped by some of the gases in the atmosphere. Water vapor being one of the important entity in the atmosphere that traps this long wave radiation, and this heats up the atmosphere from below, and that is the reason atmosphere the weather becomes cooler as you go upwards. So actually the heating happens from below rather than from above. So the differential heating over land and the ocean also drives winds. Oceanic flows are, however, primarily driven by surface wind forcing, tidal forcing, and density differences. So in the previous point, we said that atmospheric flows are primarily driven thermodynamically. Now we are saying that the oceanic flows, however, are driven by various mechanisms. One of the very important mechanism is surface wind forcing. That is, atmospheric winds, which are thermodynamically forced, now flow over the ocean, and these create surface stress on the upper surface of the ocean, which drives ocean currents. So tidal forcing is because of tides which are generated due to the gravitational pull of the sun and the moon, and this causes tidal currents in the ocean, and this gives rise to interesting dynamics. And density differences, because the temperature and salinity in the ocean changes as we go down in depth, as we change from one location to another. Density differences will create differences. This density difference can also drive the ocean currents. So now, to understand geophysical flows, first we need to at least be aware of the techniques that are available to understand, to get measurements from these flows. So this is the first thing in every domain. If you want to understand something, you need to understand their properties. So we are now discussing some techniques that we need, that people have developed over multiple decades to measure properties of geophysical flows. So first, we can use real measurements of ocean and atmospheric properties. This is done by putting a probe, for example, a temperature sensor, a salinity sensor, which is actually measured by a conductivity probe. So salinity is inferred from conductivity. And atmospheric properties, for example, you want to measure humidity or the temperature or the direction of wind, you put relevant sensors in the atmosphere. So second way to understand geophysical flows, by simulating the oceans and the atmosphere using computers. So this is very important, relevant to recent times, as computers have become strong enough to simulate large-scale oceanic and atmospheric flows, and there are various numerical models which have been developed to simulate these flows using as less a resource possible, but also keeping as much as physics possible. So I have mentioned here regional and global models. So regional models, as the name suggests, are numerical models which are specific for a certain, which are initiated, which are run for a specific region in the ocean, and global models are something which are run for the whole globe. Third, we can develop small-scale, tractable analytical models to understand the complex geophysical flows. For example, there's a phenomena that is happening in the ocean and the atmosphere, and we can have a reduced order model developed on pen and paper, and we can try to understand the properties of those that model, and then we can see whether that atmospheric phenomena, that complex oceanic phenomena matches approximately with that model. This is this is doable, but this is not always possible. For example, in a complex weather phenomena like the Indian monsoon, we cannot have a very tiny tractable analytical model which will give all the complexities of the Indian monsoon. Number 4, by conducting laboratory physical experiments to understand simplified version of complex geophysical phenomena. For example, there is a certain type of instability that is happening. We can set up a laboratory experiment and do some measurements. For example, understand the velocity field, the temperature field, and then we can say that, okay, this is what we have gained, this is the insight that we have gained from this small laboratory experiment, and then we can assume that this large scale oceanic phenomena or this atmospheric phenomena will probably behave something of this sort. Of course, we cannot introduce all the complexities, but this is a technique to understand fundamentally some of the basic process, some of the processes that constitute the big complex process that's happening in the geophysical flows. So measurements of geophysical data. So first of all, for oceans, we can have direct measurements of temperature, pressure, salinity, velocity, and other necessary or interesting parameters using fixed point sensors on buoys. So buoys are floating systems. For example, if there is the ocean surface, there's a floating body, and there are instruments on a string, and this is attached to a deadwood at the end of the at the bottom of the ocean. So we can have temperature, pressure, other properties measured. For the atmosphere, we can have fixed weather stations. You have heard of weather stations, which measure various properties, for example, water vapor, humidity, and we can also have radiosondes, which can be put up on weather balloons, and they move, they go up. So this is a fixed, fixed point measurements. So these, but whereas radiosondes on weather balloons are measurements which are moving with the wind. So so our measurements can be both fixed points and also it can be moving. For example, in oceans, we can also have moving observational platforms like research vessels, gliders. So research vessels are ships which are specifically designed to do scientific experiments on the ocean. So this is an ocean observing cruise. This is the ship Sagar Kanya, owned by Government of India, the Ministry of Earth Sciences, and this is where I went for a research trip this is shown by this on the map on the right. So this is where we started in Chennai, and then we went to position 1, and then we went to position 2, and then northward, and then we collected experimental data, of course, all throughout the cruise, and then we did some maneuver here around this location, and then we came back via this route that is being shown to 1, and then again back to Chennai. So this is an ocean observation system which is moving, which is not stationary, and the next picture shows another ocean observing cruise, and this is a recovery of a mooring. So what is a mooring, we'll get to it in a short while. So this is recovering this system. This is the floating system. I mean, this is the floating part of the system, and then there are multiple instruments below it, and this whole system is called a moored buoy or a mooring. In I mean, different people can call it differently. So there is a floating body on top, which is this thing, and this can have multiple instruments that measures atmospheric temperature or humidity, and then there are multiple instruments that measure oceanic quantities, for example, temperature, velocity, dissolved oxygen, light, the various instruments, and depending on the depth of the ocean, this wire is, I mean, we can have instruments all along this wire. So in this case, the approximate depth were about 2000 to 2500 meters, and at the end of the mooring there's an anchor so that the mooring does not drift away and it is not lost. So there's an anchor, it's a dead weight at the bottom, and during recovery there is an acoustic release. This is being released and the whole system is now free, and they are being pulled by techniques like this. So this is recovery of a mooring from a ship. So this is a stationary object. This is a stationary measurement platform, whereas a ship is a moving measurement platform. So these are some photographs from the Bay of Bengal recovery. So this is just to give you an overview of the things that I have done during the cruises that I have been. So there's a person who is there's a lifeboat, inflatable boat, which has gone to service this mooring, and this person gives you an idea of the scale of the system. So this is, as you can see, this is more than a human size, this whole system that is floating. So this was the schematic that I was showing you here in the slide. So here we'll see a video of an operation that is going on in the ship. So there are scientists and engineers in the ship who conduct experiments all throughout the day, all 24 hours of the day. And then this is a video of a person doing some measurements on the ship. And as you can see, this is raining, and the person is throwing an instrument that measures fluid properties, and this falls down under its own weight due to gravity, and while it's going downwards, it calculates various properties of the ocean water. As you can see, the ship is heaving up and down, and because of strong winds and waves. And then this is another video that shows us the recovery of a certain instrument from the side of the ship. So this is an instrument that has been pulled out of the water. And this will be brought onto the ship deck for servicing, for recovery of water samples, and then again fit in all the bottles that are here, which collects water samples, and then you can again reuse it. I mean, of course, this is a reusable equipment, and then you send it again via this arm and you drop it down into the ocean, and then you can measure various properties. You also measure temperature and conductivity, which is used to infer salinity, and also you collect water samples from different depths. So these are moving platforms, and some of these are stationary platforms. So these two distinctions are important, because we will get back to these in a short while. So fixed point sensors and moving observational platforms. So either it can be fixed, or it will or the measurements can be done on a moving platform. So these are two important concepts that we want to take it from here. So we can also do remote sensing, that is, we can remotely sense something. For example, radiometer, altimeter that measures height, radiometer emits and measures radio waves, radar, lidar, acoustic sensors. These measure properties of geophysical flows or gather geophysical data from a distance. That is why these are called remote sensing. And then we can also have some proxy measurements like ice cores, sediment cores from deep in the ocean or in the Antarctic ice sheet, to gather information of early climate or the changes in the climate that has happened over time. So this is a schematic which is showing ocean surface currents. So this is important. This is ocean, and this is the surface of the ocean. This could be a few meters to a few hundred meters, but this is a schematic which is showing the major ocean currents on an average sense. So this is not, I mean, all of the ocean, as I mentioned earlier, is a moving entity. It's not stationary, and that is the reason it makes life possible or easier in the higher latitudes. So there are various interesting properties, for example, interesting currents. So this is the Gulf Stream, this is the Kuroshio, and this is India, and there are various currents which are in the Indian Ocean, in the Arabian Sea, in the Bay of Bengal, and the Southern Ocean. There is an Antarctic circumpolar current that circles the continent of Antarctica. So in the next slide, we'll see that these currents are dynamic. They are always in motion and give rise to very interesting features in the ocean. So this is a video of surface currents from NASA's ECHO model. This uses data from satellites, in situ measurements, and numerical simulations, and this is what we see. So this is showing surface currents. This is Earth, and the you are seeing that, I mean, this will keep on rotating. It's a 1 minute video that will show various features that are happening in the ocean. As you can see, this is one of the major currents that I pointed out, and you can see that this meanders across this the coastline, and this also breaks down into small scale vortices. As the video now zooms into this region, you will see that there is swirling motions. Also there are swirling motions in other parts of the ocean, and these swirling motions are something which we call eddies or vortices, and we'll see how their dynamics can be represented, can be studied using simple laws of physics. So this was only to motivate you that the ocean is not stationary, and this is constantly in motion. So this is one of the other variables which is of importance. So this is the temperature in the ocean. So this temperature, this is showing the sea surface temperature from satellite. So as you can see, the tropical areas are hotter, which is because it receives a lot of solar radiation as compared to the other areas like the polar regions, which receive much less solar radiation. So this is the ocean surface temperature, and the scale is in degrees Celsius. As you can see, it has a broad range. For example, it goes from -5 to approximately 35, 36, 37 degrees centigrades. So now there is one more interesting parameter, which is ocean salinity. So this is again a satellite map of surface salinity, that is salinity at the surface of the ocean, and this is showing various regions, and this goes from a scale of 33 to 38, whereas there's various regions, for example, in the higher latitudes and near India in the Bay of Bengal, these go to very small salinity values. Hence this scale is not doing justice properly, but let's use this figure just to appreciate the fact that salinity, that is the salt content, can be variable across the globe, and these regions, as you can see in the Atlantic, are one of the most saltiest because of high rate of evaporation, and some of these regions, for example in the Bay of Bengal, receives a lot of fresh water from river which actually are fed by monsoon rains and melting of the glaciers, and this is why these regions are this region is much fresher, that is, it has low salinity. So now coming to atmospheric variables, this is an image taken from the India Meteorological Department's website. This is showing moisture or water vapor content in the troposphere. So the dark regions show that the area is of high temperature and it is dry, whereas the bright regions show that these are of lower temperatures and they're moist and it has clouds. So such images also provide some information about the swirling motions that you can see. I mean, you can almost see that there are these places, for example, which bend, and these kind of images also give us some ideas about jet streams. The jet streams are streams of air that approximately flows at around 10-15 kilometers away up from the surface, and these flows mostly towards the eastern direction. So the reason why I showed various variables that were obtained from models, from satellite measurements, from direct measurements, is to appreciate the fact that these measurements are measurable, and these are the measurements that we will keep on using in our studies to understand how these flows evolve over time. So of course we'll do very simple analytical models, and we will also use we'll also see how computer simulations are used towards the end of the course. But this is important for us to appreciate that there are various measurable quantities which we can then plug into a computer, or we can plug it into a mathematical model, and then we can understand the dynamics of these flows better. So temperature, salinity, velocities also vary with depth in the ocean. I showed you only surface properties, but these also vary with depth. But temperature, for example, decreases with the ocean depth. Salinity increases generally with ocean depth. So this is depth of the ocean, and this is temperature, this is salinity. These are just some average representative properties of or profiles of temperature and salinity variation. The temperature and velocities also vary with height of the atmosphere. As you saw, we have troposphere and stratosphere, and temperature varies differently in both of these layers, and of course going into higher layers of the atmosphere, this varies in different ways. So these are not the surface variables as shown in the previous slides only give us information about the surface of the ocean, or the variables at a certain height, but these also have a depth dependence. So very briefly, these are some scales of motion in geophysical fluid dynamics. So the first four are for the atmospheric phenomena, and the bottom four are for some phenomena that are observed in the ocean. So these are just representative phenomena, and these scales, as I mentioned, are approximate. So these are not exact scales. This can vary even by an order of magnitude. This is just to give you an understanding of how much variations can occur. So for example, thunderstorms can be a few kilometers. Cyclones can be a few hundred kilometers and go up to 50-60 meters per second, and they can last for a few days. Weather phenomena can be a few thousand kilometers. This can have speeds of 1, 10 or few meters per second, and this can exist for a few weeks. Whereas climatic variations are global scale, that is, affects the whole globe, and these are very small velocities, and this can exist for multiple years to decades. Whereas on the other hand, oceanic phenomena, for example, internal waves, we'll get to what are internal waves as we go deeper into the course, and are of the order of few tens of kilometers to hundreds of kilometers, and they exist for minutes to hours. And there are other features, for example, tides, which arise due to gravitational attraction of the moon and the sun, and eddies, which are swirling vortices that you saw in the previous video, or the ocean currents, the Kuroshio current that I mentioned, the Gulf Stream that I mentioned. These are of various length scales, some few meters per second, and this can now exist for hours and days to weeks, and weeks to seasons. So these are just some representative velocities and length scales and time scale of the phenomena that can happen in the atmosphere and the ocean.